All right, ready to get in some serious data crunching today?
Always up for a challenge.
Good, because we're talking about shrinking those giant vector
The
databases.
ones powering things like image search, right?
Exactly. And the goal is to do it without sacrificing any accuracy.
That's a tall order. Where do we even start?
Well, we've got this research paper plus a whole bunch of FAQs and study guides.
So a real deep dive then,
By the end, you'll not only know what these techniques are, but why they're a big deal.
especially with these databases just exploding in size.
Okay, to set the stage, we're dealing with vector databases. Images, videos, they're all turned into vectors.
Basically coordinates in multi-dimensional space so you can find similar items.
Right, but as these databases hit billions of items, storing and searching them gets computationally expensive.
Even with methods like product quantization.
So this research tackles something different. Instead of compressing the vectors themselves,
They're looking at compressing the extra data around them, losslessly.
things like the IDs and how they're organized,
And that's where it gets interesting. They realize that in common search structures
like inverted files.
and graphs, the order of the vector IDs within a cluster or list doesn't matter.
Hold on, back up for a second. For those of us who haven't really thought about database structures,
Sure.
what exactly is an inverted file?
Think of it like the index at the back of a textbook. It tells you where to find specific words.
Okay,
An inverted file does the same, but instead of words, it points to vector IDs.
so instead of listing pages where cat appears, it lists IDs of cat pictures,
Exactly. And the same idea applies to graphs.
where nodes are data points and the connections are relationships.
Like a social network, each person is a node, and their friends are the connections.
Gotcha.
Now, back to the order of the IDs. Rearranging them within a cluster or list doesn't change the underlying information.
It's like shuffling someone's friends list on their profile. The connections stay the same.
Exactly.
So they're saying we can toss out the order information and still search effectively.
Right. And according to information theory, that means we can represent those sets of IDs using way fewer bits.
Like compressing a file, but for a whole database of IDs.
Precisely.
So how do they actually compress these sets of seemingly random IDs?
They explored several techniques based on this orderless compression. One of the most powerful is asymmetric numeral systems.
ANS.
Yeah, ANS. It's a way to encode data based on probabilities, shorter codes for frequent patterns, longer codes for rare ones.
Like Morse code, short signals for common letters, long ones for less common letters.
Similar, but ANS is much more sophisticated. And here's the kicker. They managed to apply this not just to the IDs themselves,
But to the already compressed codes representing the vectors.
yeah, a bonus round of compression, squeezing out every last bit of redundancy they can find.
Wow. But the real question is, how does all this compression affect search speed?
Well, that's the surprising part. They found these techniques had almost zero impact on search speed, especially when combined with methods like product quantization, which already have some computational overhead.
So smaller database, but no performance hit. That's amazing for anyone dealing with massive data sets.
It does make you think about how much data we've been storing unnecessarily. But to get the full picture, let's break it down how they actually applied these compression techniques.
Okay, you mentioned ANS, but there are other terms floating around earlier. Bits back coding, ROC, and REC. Can you unpack those for us?
Absolutely. Bits back coding is this clever trick that involves a hidden variable, something that influences the data but you can't directly observe. By sampling this hidden variable, you can achieve impressive compression. It's like trying to compress a book. Instead of encoding each word, you encode the underlying topics, which is more compact.
So for our cat picture database, the cat theme itself is like a hidden variable, influencing which pictures are grouped together.
Exactly. Now, ROC, which stands for random order coding, uses this bits back approach specifically for sets and multisets. It exploits the fact that the order of IDs within those sets doesn't matter for better compression.
So ROC is basically saying, I don't care if those cat pictures are in alphabetical order or by upload date, I just need to know they belong together.
You got it. And REC, or random edge coding, does the same thing, but for graph data. Remember those friend lists we talked about? REC treats the order of friends on each list as a hidden variable, which lets it compress efficiently without losing connection information.
All right, I think I'm starting to see the bigger picture now. But there was one more piece you mentioned earlier, those wavelet trees. What role do they play?
Ah, yes, the wavelet tree. This is where things get a bit more technical. Imagine a tree structure. Each node represents a subset of IDs in your database. The root node is all the IDs, then it branches out, smaller and smaller subsets, until you get to the individual IDs at the leaves.
So like a family tree, but instead of people, it's all the cat picture IDs.
Exactly. The wavelet tree encodes this structure using binary strings. By following these strings, you can pinpoint any ID within the compressed data without decompressing everything else.
So it's like a map that guides you straight to the cat picture you're looking for, even with the entire database compressed.
Precisely. And because it's a tree structure, the search process is incredibly efficient, even for huge databases.
But all this complexity must come at a cost, right? Doesn't using these trees slow down the search?
There is a slight trade-off. Wavelet trees do introduce some computational overhead compared to the other techniques, but the advantage is you get full random access to any ID, which is crucial for some applications.
A balancing act between speed and flexibility, then. But what about the overall impact of these compression methods on search performance? Did they actually test this on real-world data?
They did. They applied their techniques to a billion-scale dataset using a state-of-the-art vector compression method called Q-in-Co. The results were impressive. They achieved a 30% reduction in the overall size of the index.
Whoa, 30%. That's massive. Does that mean you could fit a database 3 times larger on the same hardware?
Theoretically, yes. And they did it without any noticeable impact on search accuracy or speed.
That's remarkable. Sounds like these techniques have the potential to revolutionize how we handle massive vector databases in all sorts of applications.
Absolutely. From image search to recommendations to drug discovery, genomics research, efficiently compressing and searching these massive data sets is becoming crucial. But as with any new tech, there are potential challenges and limitations to consider.
Okay, let's talk about those. What could hinder the widespread adoption of these techniques?
Well, one thing is the researchers mostly focused on static data sets, where the content doesn't change much over time.
Right, so how do these techniques work in more dynamic environments, like e-commerce or social media, where new data is constantly being added?
That's the key question. If the data patterns are shifting, the compression models might become less effective, might need frequent recompression.
So it's not a one-time compression and you're done. You might need to constantly adjust the compression scheme.
Exactly. And handling updates to the database itself can be tricky. Adding or removing items might require recompressing parts of the data, could cause delays and overhead.
Makes sense. Any other potential drawbacks we should be aware of?
Another thing is the computational cost of compression and decompression. The research showed minimal impact on search speed in their tests, but real-world scenarios with complex queries, different data distributions, it could be different.
So the overhead might be noticeable with more complex searches when the data isn't as neatly organized.
Right. And the performance gains can depend on the specific hardware. These techniques rely on bit manipulation, efficient memory access, so architectures optimized for that, like GPUs, might see bigger speedups.
So it's not just the algorithms, but also how well they work with the hardware.
Absolutely. The interplay between algorithms and hardware is key for optimization.
It seems like there's still work to be done before these techniques are widely used.
There's definitely ongoing research addressing these challenges. For example, the researchers mentioned looking into approximate calculations within the Fenwick tree used for ANS coding.
To speed things up.
Yeah, potentially, but at the cost of slightly lower compression rates.
So it's a trade-off. Speed, efficiency, accuracy.
Always is.
Even with these challenges, this research has opened up some exciting new possibilities for dealing with the ever-growing flood of data.
Definitely. It reminds us that sometimes the biggest innovations come from finding clever ways to exploit the structure of data, even if it means challenging old assumptions.
Well, this has been a fascinating look at how researchers are pushing the limits of data compression without sacrificing search performance. We covered a lot, from the techniques to the potential challenges.
As these techniques evolve and get used in real-world applications, it'll be interesting to see their impact across various fields. Faster image recognition, more personalized recommendations, faster drug discovery. The possibilities are huge.
Big thanks to our listeners for joining us on this deep dive. We hope you found it insightful. Until next time, keep exploring, keep learning, and keep diving deep.